Hello children, physics explains the law of nature in a specific way. This explanation includes a quantitative measurement, comparison, and measurement of certain physical quantities. To measure a physical quantity, we need to have certain standard units. For example, same volume of iron would be heavier than the same volume of wood, or we can say same volume of iron will have more density than the same volume of wood. But why and how? To explain this, I have come up with a new chapter, that is chapter number 2 of your course book, Physical Quantities and Measurements.
All objects around us have two things in common. They have mass and volume. Everything that has mass and volume is matter. The mass of an object is a measurement of the amount of matter it contains. The greater the matter of an object, the greater its mass. Mass is measured in kilograms or its derived units. The volume of an object is a measurement of the space it occupies. The greater the matter of an object, the greater its volume. Volume is measured in cubic meters or its derived units. On the other hand, density is the ratio between mass and volume. It is a property of materials, since each material has its own specific density. Therefore, different objects made of the same material always have the same density, regardless of their mass and volume.
So from this video you have learned about mass, volume and density, and how to find the density using the formula density is equal to mass upon volume. That means by finding the mass and the volume we can determine the density of an object. So now let us define density. Density is defined as mass per unit volume. Next is units of density. In SI system, mass is measured in kilograms and volume in cubic meters. This you have studied in your previous class, in class 7th. Therefore, the unit of density in SI system is kilogram per meter cube, whereas the unit of density in CGS system is gram per centimeter cube. The next topic is to determine the density of a solid by using a measuring cylinder. In order to determine the density of a solid, we must know the mass and the volume of the solid. Let us say that we have to find out the density of a stone. So first of all, we can find its mass very easily by the help of a physical balance. Physical balance can help us to find its mass very accurately. Now, to find the volume, we'll take a measuring cylinder and we'll pour in it some water. We will record the volume of the water from the graduations marked on the measuring cylinder. Now we'll take the stone and we'll tie a fine thread to it, and we will lower it gently in the measuring cylinder so that it gets completely immersed in water, and we will record the new level of the water. So now to find the volume of the stone, we will subtract the initial reading from the final reading, and we will get the volume of the stone. So we have found the mass of the stone, we have found the volume of the stone, so we can get the density by the formula density is equal to mass upon volume. Now you can understand this topic very easily with the help of this video.
To measure the volume of an irregularly shaped object, such as a rock, measure the volume of the liquid displaced when the object is submerged. To do this, measure the initial volume of water in a graduated cylinder. Submerge the irregular object and measure the final volume of the water. The difference between the initial volume and the final volume is the volume of the object. In this example, the initial volume is 50 milliliters. Dropping the rock in the graduated cylinder causes the water level to rise. The final volume is 81 2/10 milliliters. To find the volume displaced, subtract the initial volume from the final volume. Doing so yields 31 2/10 milliliters. So the volume of the rock is 31 2/10 milliliters. Typically, the reason to measure the volume of an irregular solid is to determine the density of the solid. Density is the mass of a substance per unit of volume. The formula for density is mass divided by volume. You could also find this formula by looking at the formula chart. Using a balance to measure the mass of the rock, we determine that it is 74 88 grams. Since we know that the volume of this rock is 31 2/10 milliliters, and the mass of the rock is 74 88 grams, we can calculate its density. When we divide the mass by the volume, we arrive at 2 4/10 grams per milliliters as the density.
Now we will learn about measurement of density of irregular solid using Eureka can. A Eureka can consists of an iron vessel which is provided with a spout. Fill the Eureka can with water till the water is at the point of overflowing. Under the spout of Eureka can, place a measuring cylinder. Gently lower the solid in the Eureka can. The solid displaces water which flows out from the spout into the measuring cylinder. Record the volume of water overflown. This gives us the volume of the solid. The mass of a solid is determined by a physical balance very accurately. Now, knowing the mass and the volume of the solid, the density can be calculated by the formula density is equal to mass upon volume. You can watch a video now which will help you to understand the topic very well.
So today I'm going to perform an experiment to find the density of the irregular shaped object, solid object, that is stone here. So this is the stone whose density I wish to find out, and for this entire experiment I require a Eureka can. So basically this is Eureka can method to find the volume, then we are going to find the density. So this is an Eureka can. As you can see, this is made up of copper, and this Eureka can be maximum be filled till here. As you can see, there is a hole here, so through which the extra water can flow out. So maximum you can fill the water till here. So if I keep the Eureka can till here, the water level can be filled till here, because even an attempt to fill the extra water, the water will overflow from here. As you can see that this Eureka can doesn't have any kind of graduations, right? So other things that we require is a small beaker with graduation. Now I have also a measuring cylinder which has got more number of graduations on it, so I can measure the accurate volume. And to measure the mass I require a electronic balance. What I have done is I have tied this stone with a very thin thread, and now I would be gently lowering it inside the water in the Eureka can. The formula used in this experiment is very easy, people. So we know that density is equal to mass upon volume. So I would be finding the mass of the stone with the help of this electronic beam balance, and the volume shall be measured with the help of the Eureka can. So let's begin the experiment. Okay, so now I'm ready to perform the experiment. So here is the empty Eureka can, and as I said that we are supposed to completely fill it, and any extra water after it gets completely full will come out in this particular beaker. So I'm going to add some water. As you can see that the extra water is overflowing out, and I must ensure that this Eureka can should be completely full. So now almost the extra water has been taken out in this beaker. Now I would be taking another beaker over here with some graduations on it, and I'll be putting it over here like this. Now as you can see, the readings are 20, 40, 60 and 80. Till here it is 100 ml. So let me gently lower this stone. So this is the stone whose density we wish to find out. So first of all I will immerse this stone completely, and the water which will be displaced out will be collected over here, and we know that the volume of the water displaced out will be equal to the volume of the stone. Yes, there is a very little bit error in this experiment because the thread contains very small volume, so it will also displace some extra volume of water equal to the volume of the thread, but that is very negligible. We can actually neglect that part. So now I am immersing this stone, and as you can see, you have to be patient in this experiment. Let the water get completely displaced out. Now I have a problem with this apparatus, because the problem here is the volume is in between 20 and 40. So I don't know whether the volume over here is 25 or 27 or 30. So in order to accurately measure, I have this measuring cylinder which has got good number of readings over here. So let me pour this water over here. Now this reading says that the volume is 31 ml, people. It might be very difficult for you to see, but this is 20, this is 30. Now when I keep it straight, the water level is just above it and the reading shows as 31 ml. So now I know the volume of the stone is equal to the volume displaced, and that is 31 ml. So now let me note it down. So the volume of the stone was 31 ml, and we know that 1 ml is equal to 1 centimeter cube. So this is 31 centimeter cube, that is the volume of the water displaced, same as the volume of the stone. Now I would be measuring the mass of this stone with the help of the electronic beam balance. All set. Now this is the stone whose mass I am supposed to find out, and I have removed the thread from it. So the reading says that the mass of the stone is 63.2 grams. So let me note it down. Now since the mass of the stone was 63.2 grams, so let me put the value over here. 63.2 divided by volume is 31. So let me calculate it. 63.2. So this is 63.2 divided by 31. The answer is 2.038. So that means the density of the stone is 2.038 grams upon centimeter cube.
This completes today's session for the chapter. The assignment in the form of PDF has been given for this chapter. The same lesson will be continued in the next video. Till then, take care. Bye bye.